Hello everyone, welcome back to my channel. In this tutorial, we will learn Linux and High Performance Computing, or HPC, for biological data analysis. We will begin with basic Linux commands and gradually move toward running a real bioinformatics analysis on an HPC cluster. In the first step, we will learn how to use the Linux terminal and navigate through files and folders. The terminal allows us to communicate with the computer by typing commands. When working with bioinformatics data, we normally use the terminal to organize files, run software, execute scripts, and analyze our results. Check your current location. The first command is pwd. It stands for print working directory. The ls command displays the files and folders present in our current directory. The L option displays detailed information, and the H option shows file sizes in a human-readable format. To display hidden files, LSLUR option also displays hidden files. In this step, we will learn some essential Linux commands used to organize files and directories. We will create a small project directory for this tutorial. We will use the same project in the remaining steps. First, I create a new project directory called Linux_HPC_tutorial. Then I move into that directory using the cd command. Finally, I use pwd, which stands for print working directory, to confirm my current location. Next, I create 4 folders to organize my project. The data folder will store input files, scripts will contain bash or analysis scripts, results will hold output files, and logs will keep log files. With LSLH, I can view detailed information such as file permissions, owner, size, and modification date in a human-readable format. The cp command creates a duplicate of the file. Here, I copy example.txt and save it as example_copy.txt. Running ls again confirms that both the original file and the copied file are present. Next, I use the mv command to move example_copy.txt into the data folder. Finally, I copy the original file into the data folder. Unlike the mv command, cp leaves the original file in its current location while creating a copy in the destination folder. Last command we'll learn is room, which stands for remove. Now that we know how to create and manage files, let's learn how to view, search, and inspect them. These commands are used constantly in bioinformatics because most analyses begin by checking input files. First, I move into the data folder where my sequence files are stored. Running ls shows all the files available in this directory. Here I am using the v-editor to create or edit a file called sequences, data. This file contains a few example DNA sequences. Using the cat command, I can display the complete contents of the file. Head command displays the first 10 lines of the file. You can also specify exactly how many lines you want to display. The tail command displays the last 2 lines of the file. Finally, I use the clear command to clean the terminal screen. The WCL command counts the total number of lines in a file. Grep command searches for specific text inside a file. In FASTA files, every sequence starts with the greater than symbol, or greater than sign, greater than. This command lists all sequence headers in the file. The C option counts the number of matching lines instead of displaying them. Next, I move into the scripts directory, where I'll store my bash scripts. Finally, I create a new bash script named sequence_summary.sh. I'll write a simple bash script that counts the number of sequences in a FASTA file. The first line is called the shebang. It tells Linux to execute this script using the bash shell. I'll open it using the V-editor. Now let's verify that the script has been created. At this point, the script is just a normal text file. To make it executable, I use the chmod command. The +X option adds execute permission. Now let's execute the script. Now that we've learned how to work with files, it's time to automate our tasks using bash scripts. Here, I run the script using /. This tells Linux to execute the script from the current directory. As you can see, the script starts successfully. It displays the input FASTA file, counts the number of sequences, and finally prints the completion message. You can also execute the script by calling the bash interpreter directly. This method works even if the script doesn't have execute permission, as long as the file is readable. Now that we've learned the Linux basics, it's time to move to a high-performance computing, or HPC, cluster. To access an HPC system, we use the SSH or Secure Shell protocol. SSH creates a secure connection between your computer and the remote cluster. Before submitting the job, let's quickly review our SLURM job script to make sure everything is correct. Cat command displays the entire contents of the script. Here we can verify the job settings, requested resources, and the analysis commands that will be executed on the compute node. Once the script looks correct, it's time to submit it to the HPC cluster. The sbatch command sends the job to the SLURM scheduler. After submitting the job, we can check its status using the squeue command. Here you can see the job ID, job name, user, current status, runtime, and the assigned compute node. In this example, the job status is PD, which stands for pending. When resources become available, the status will automatically change to R, which means the job is running. Once the job has finished running, the final step is to verify the output. If your job is no longer listed, it usually means the job has completed successfully. You can also see the results folder, where the output generated by the job has been saved. Here, you can see the output file named sequence_count.txt, which was created by our SLURM job. Finally, I'll display the contents of the output file. As you can see, the result is 3, which means our script successfully counted 3 sequences in the FASTA file. Now that we know how to use Linux and HPC, the next step is learning how to manage bioinformatics software. On an HPC system, you usually don't install software yourself. Instead, you load pre-installed software using environment modules, or you create your own software environment. View all available modules. This command displays all software modules available on the cluster. Since we're looking for FastQC, I scroll through the list until I find the FastQC module. As you can see, the available version is FASTQC 0.11.8. Load the FastQC module. Verify the installation. If the version number is displayed, it confirms that FastQC has been loaded successfully and is ready to use. Congratulations! Party Popper, you've successfully completed this Linux and HPC for Bioinformatics tutorial. If you found this video helpful, please hit the like button, subscribe to the channel, and turn on the notification bell so you don't miss future bioinformatics tutorials.